In the previous video, we talked about how various different forming processes, such as forging, extrusion, and drawing, actually cause the piece of material to work harden when it's processed. Now, this work hardening is as a result of plastic deformation, and although it's called work hardening, hardness isn't actually the only property that's affected. We can see from our diagram on the left-hand side here that when the piece of material work hardens, or when it's worked, the hardness increases as we'd expect. The strength increases alongside the hardness, but we see a reduction in ductility and we see a reduction in grain size. Now, each of those properties are changing with respect to the amount of cold work that's being done. Now, just to put that into context, the amount of cold work being done is a measure of how much plastic deformation is occurring. So, for example, in a drawing process, we might want to reduce the cross-section by 25%, and that would lead to a certain amount of cold work being done. However, if we wanted to reduce the cross-section by 50%, then more cold work would be done on that piece of material. It would undergo further plastic deformation. So this is a measure of how much plastic deformation is being done. We see hardness increase, strength increase, and ductility decrease. We also mentioned a process called annealing. And annealing is a heat treatment process that's used to recover the properties of the material after work hardening. So on the right hand side of this diagram, we can see how each of those properties is recovered during this process. Now, there's a couple of things that affect this process and how fully the properties are recovered. The first is the temperature, and we want to raise that piece of material above its recrystallization temperature. Now, it's important to point out that we're not melting that material, it's still in the solid state, but we're raising it to a temperature where recrystallization can occur. Once we've heated the material, we do something called soaking. And soaking is holding the piece of material at that new temperature. So in effect, we're elevating the temperature of the material, and then we're holding it at that new temperature so the atoms can rearrange themselves. Now, once we've heated the material and soaked it at the new temperature, we then allow the material to cool. And there's a couple of different ways that can be done. During annealing, the material is going to be cooled very slowly in the furnace. So the temperature of the material is going to be reduced very, very slowly to allow that full recrystallization to occur. There's an alternative process called normalizing. And in normalizing, we actually allow the piece of material to cool in the air, or at air temperature. The difference is when we normalize the material, the cooling is much quicker than when we anneal the material. And the different cooling times will affect the degree of recrystallization. So if we can afford the time and we want full recrystallization or full restoration of those properties, then we would anneal the material. If we only need partial recovery, or if time's an issue, then we may choose to normalise the material. But for the purpose of this video, when we anneal the material, we cool it gradually in the furnace. Now, if we look at the start and end points of each of those graphs, we can see hardness, for an example, starts and ends at the same point, meaning after the annealing process, the property has been fully restored, and we see the same for each of the other properties. So at the end of the annealing process, the material is restored. Let's look at this annealing process in a little more detail. And on this diagram, we only have two of the properties displayed. We have the tensile strength and we have the ductility, but we know that the hardness and the malleability are also going to change accordingly. So as we anneal the material, the strength reduces and the hardness reduces, and as we anneal the material, the ductility and malleability is going to increase. Once again, in this view, we can see that the annealing temperature has an impact on the amount of recrystallization. This diagram here is for brass. Now, if we refer to the section of the diagram in the centre here, we can see what happens as a result of cold work. We see that the grains of our material have been disrupted. And this will be as a result of the dislocations caused by plastic deformation. Now, when we anneal that material at different temperatures, what we're trying to do is restore the large grains that we see on the right-hand side. So at lower temperatures here, we don't really see the grains reforming, but some of the internal stresses will be relieved within the material. As those internal stresses are relieved, we see some recovery of the material properties. Now when we get to higher temperatures, we see that the grains begin to reform. And we'll look in a bit more detail at that process in a moment. And then at the higher temperatures, we have the larger grains forming. And when we have larger grains, we have large sections of the material where we have a neat crystalline regular structure. So the question is, why do the atoms rearrange themselves at the recrystallization temperature? What we see in this view is a grain boundary between two grains. So we have a grain boundary here. And when we heat the material above its recrystallization temperature, atoms within those grains are able to move. So recall that at low temperatures, all we're doing is relieving stress around the dislocations, but at higher temperatures, recrystallization is occurring. And when recrystallization occurs, we see these grain boundaries move. So atoms from one grain diffuse across the grain boundary into the next grain, and in doing so, they align themselves with the atoms in the new grain. So over time, we get new grains formed, or at least we get the movement of grain boundaries, and over further prolonged periods of time and at higher temperatures, each of those grains are actually going to expand. So we're going to see a reduction in the number of grain boundaries as each of those grains expand. So the important things here are as follows. At lower temperatures, we see recovery. And recovery is where we see reductions in strain energy and some of the properties begin to restore. But we can see from the diagram at the top that the tensile strength isn't recovered a huge amount during that phase, and neither is the ductility. It isn't until we get into the recrystallization stage and each of those grains begin to reform that we see significant recovery of those properties. So during recrystallization, we see the tensile strength reduce significantly and the ductility increase significantly. And finally, when each of those grains begin to enlarge at the higher temperatures, we continue to see a small amount of additional recovery of those properties. The vast majority occurs during the recrystallization stage, when each of those deformed grains is given the opportunity to reform its neat crystalline structure.